Suggested you bring your calculators, but as it turns out, you won't need your calculators yet today. Sorry. Today I just want to, and we'll be talking more about units as we go, but I want to get to scientific notation a little bit, and I guess you don't need your calculators for that.
I have a Casio calculator that's like, it's like 10 years old, but it has some scientific stuff on it.
Okay.
I don't think it's programmable.
I could take a look at it. Probably okay. But in science, we need to be able to measure things, and we're going to talk about, we'll definitely be measuring things in the lab, and working problems with measurements. But the thing about measurements is what we do here in the United States, we're definitely a worldwide community when it comes to science and exchanging things and materials, so we need to have kind of a common reference standard across the world. So in general, there's different things you can measure about an object. You can measure an object's mass, and in general, that's how much matter is contained within that object. You can measure dimensions of length of an object. That's generally the distance between 2 points. You can measure the volume. That's basically how much space an object is occupying. You can measure the temperature of an object, and we'll be talking more about temperature and heat. But temperature is not the same thing as heat. Temperature, one of the things temperature does do is tell you the direction that heat will go. So for instance, when it's nice and toasty in your house and you open up your door to the outside, which is cold, heat is going to go from warm to cold. Okay, that's kind of how it does. So heat is energy, but temperature is just an indication of energy. So these are things that you can measure. There are more things that you can measure. But with regard to kind of a standard, a worldwide standard that everybody can go back to, in Paris, France, and I've got a figure from your textbook or a photo from your textbook that shows you what this looks like. But there's like a weight that everybody's balances are traced back to. Okay, so out in factories, a lot of times they will come and they will calibrate your scales, and the weights that they use to calibrate your scales need to be traceable back to some common standard. With regard to length, to make sure we're all kind of on the same page worldwide, length goes actually to a phenomenon which is awesome, that light travels at a distinct speed. So the speed of light is about 186,000 kilometers per second. Here it is, yeah. Here it is in terms of how long does it take to travel 1 meter? That fraction of a second. So you can actually calibrate, we wouldn't, but you can calibrate length that way by how fast light travels. Volume is calibrated back to length. We're gonna, when we get started, I'm hoping we can do this sort of thing, where if I were to give you the shape of a cube, okay, a cube is the same on length, width, and height, okay, length, width, and I don't know, I guess height, maybe here, this might be width, this might be height. Anyway, those 3 unique dimensions, to find the volume of that, we would take length times width times height. And if we were measuring the length and the width and the height in terms of meters, we could maybe have a cube that's 1 meter by 1 meter by 1 meter. And as we get to working problems, one of the things I'm going to emphasize is we take the number, which is 1, and multiply the number times each other. 1 times 1 times 1 is 1. And then we take the units and multiply those times each other. So meters times meters times meters is equal to meters cubed. Yeah, meters raised to the 3rd power. Okay, so volume goes back to length. Cubic length is great for volume. Time goes back to energy, and not light necessarily, but a microwave energy that's emitted by this particular element, cesium. Temperature goes to the triple point of water, which is about, I looked it up this morning, it's approximately 0.01 degrees Celsius. So about 0 degrees Celsius, 273.1 of that is 1 unit is Kelvin. And then amount in chemistry, when we get rolling, if we're talking about like a substantial amount of molecules, we don't want to talk about a dozen molecules because that wouldn't be very many molecules. Instead, we talk about like a mole of molecules. So a mole of molecules, as some of you guys may already know, is, and we're talking about scientific notation today, 6.022 times 10 to the 23rd. That's 1 mole. 1 mole of anything. Okay. So it's a pretty big number. But when we talk about amounts, that's what we do. There is the iridium alloy metal that's, actually this is just a model of it that's here, but it's a model of it like what is kept in Paris, France. With regard to units of measurement, we're going to go metric, which might be a little change for some of you guys. But in the metric system, okay, actually, I've talked about we need to be global about what we do in science. And so measurements, there are a group of measurements called international standard measurements, and they're metric. So the basic unit of length is a meter. The basic unit of mass is not the gram, it's the kilogram. The basic unit of time is the second. Of temperature is the unit Kelvin. We'll be talking more about that later. But these are international units. Probably recognize some of this glassware that we've been using in lab. So remember those little white marks are gradations. If you're after volume, this is all about volume, what this slide is. If you're after volume, notice that when you guys grabbed your graduated cylinder and used it yesterday, you were getting more precise measurements, more precise volume than if you were just to take the volume marks on your beaker. So kind of intuitively you would say that. This right here is called a pipette, and it also measures volume, but it's only one set volume for this pipette. Up there is a calibration mark. Okay, so it's pretty darn precise. This is also precise right here. This containing the yellow solution, that is a volumetric flask. Again, it has just one mark. And this we may get to use later. It's called a burette. And this one has like little gradations going up. Pretty precise. And you dispense your liquid down here. Okay, so let's see, this should play. Bless you. So again, kind of back to the metric system, we'll do a lot with regard to mass. We'll be working with grams. Notice that it's a lowercase g. Meters is a lowercase m for length. Okay. Liters, volume is an uppercase L. And seconds we won't be working much with, but it's just the letter S, lowercase. Cubic meters, like I kind of made the little meter cubed thing a minute ago, would be lowercase m raised to the third power. So the whole capital or lowercase is important. And we don't use, even though we're tempted to, we don't use the little period after it. And even though you're tempted, so for instance, if you weigh out 2.3 grams, you might be tempted to do a GS or something, GMS, but it's just 2.3 grams. So just kind of an introduction to measurement and some units. Okay. I'm not gonna, like, you won't have a homework with metric prefixes yet, but you will later, so kind of listen up. So we're going to use the metric system, and you see a bunch of prefixes over there to the left. You won't need to memorize all of these prefixes. I've put boxes around the 4 main ones. Okay. So notice the 4 main prefixes. One of them is bigger than what we say the base unit, prefix kilo. It means 1,000 times what we call the base unit. Centi, just like 100 cents, it makes $1. Okay, centi means 1/100th of the base unit. Milli means 1,000th of the base unit. And micro means 1/1,000,000th of the base unit. So this is 1/100th. This is 1/1000th. And this is 1/1,000,000th. With what, 6 zeros, right? So again, we'll be talking more in just a minute about this whole kind of, I feel like it's packing things up into scientific notation, okay, coming up. But notice that if you have a negative exponents of scientific notation, that means a number that is less than 1. If you have a positive exponent, that means a number that's greater than 1. All right. So again, kind of looking at prefixes. Kilo, you'll need to know that. It means 1,000 times the base unit. Centi was 1/100th. Milli is 1/1000th. Micro is 1/1,000,000th. So this is just kind of an introduction, picking on the prefix centi and picking on the length as meters. So 1 centimeter is 1/100th of a meter. So if you're like me, the fraction kind of drives you nuts. Okay, so we can get rid of the fraction 1/100 if we multiply both sides by 100. So that's kind of what I'm showing you here. Multiply both sides of the equal sign by 100. 100 here and 100 there. And then what happens with these 200s? Yep, they cancel out, exactly. So I could rewrite this, and I could say 100 centimeters is equal to, since these cancel, 1 meter. So this little kind of thing I've done here is just to kind of show that these are called equality statements. This is to show that we could say that if we're trying to link centimeters and meters, we could say that 1 centimeter is equal to 1/100th of a meter, or we could say that 100 centimeters is equal to 1 meter. Either way. And we'll definitely, within the metric prefixes, we'll be doing some problems like that down the road too. These are called equivalency statements. Okay. So a few more equivalency statements. If I put an arrow like this, that means that's something you need to memorize. So you're going to want to memorize that 1 inch is exactly equal to 2.54 centimeters. Okay. Now there are more inexact relationships than exact relationships, and actually that's just kind of the way they set it up. So it's what we say by definition. These you don't have to memorize. Okay, 1 inch is exactly equal to 2.54 centimeters. That's the length. That's the link for length. Okay, a length for volume would be, for instance, between the English and metric system, 1 gallon is approximately equal to 3.785 liters. 1 pound is approximately equal to 453.6 grams. You don't have to memorize those. Another one you need to memorize, now this would be within the metric system, because liters are metric and meters are metric. There's this cool relationship between milliliters and centimeters cubed, and that's a 1-to-1 relationship. So 1 milliliter is exactly equal to 1 cubic centimeter, so you're going to want to memorize that. They're both volume, right? All right. So this whole idea of taking a number and packing it up into scientific notation. So we've already seen, like this morning, some powers of 10. for instance, a little bit ago, you know, you saw 1,000. In terms of a power of 10, it's 10 raised to what power? Mm-hmm. Very good. And you saw powers of 10, 1/1000th is equal to 10 raised to what power? -3. Yep. So that's powers of 10. And we're going to use that to our benefit to pack up big numbers or small numbers. Because in chemistry, we deal with both, big and small. This idea of, if you've taken other science classes, the teacher tries to tell you how to round your number. Like if your calculator displays like, you know, 3.567297, blah, 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 blah. Your teacher says, don't write down the entire number. And he or she is telling you how to round it, and we'll talk about how to round it. Actually, if you pack up a number in scientific notation, it's an easy way of showing how you rounded it. And how you rounded it is according to significant figures. So, scientific notation numbers that have been packed up in scientific notation have two parts. They have what I call the decimal part, and then they have the power of 10 part, or the exponent part. So when I wrote like 10 to the third is equal to 1,000, or 10 to the negative third is equal to 1/1000th, that would be the second part. So your decimal part always needs to be at least 1, but less than 10, your decimal part. We call that the coefficient. I don't know if that's on the later slide. Coefficient is this part. The exponent part, 10 raised to a power, it can be positive or negative, right? Because we just kind of saw a couple examples of that. If it's positive, it's going to be a big number that you packed up. If it's negative, it must be a small number that you packed up. It can also be 0. And I have a slide as much, but 10 raised to the 0th power, anything raised to the 0th power is 1. Exactly. Very good. All right. So 10 raised to the first power is 10. Okay. 100 can be broken down as 10 times 10, which is the same thing as 10 squared. 1,000 can be broken down as 10 times 10 times 10. 10 raised to the third. 10,000 is 10 times 10 times 10 times 10. 10 raised to the fourth. 10 raised to the fifth is 100,000. Okay. You're probably fine with that. So 0.1, and usually I put the 0 there because that kind of emphasizes where my decimal is. Okay, that 0 doesn't do anything, but again, it emphasizes that decimal. So 0.1 is 1/10. 1/10 can be written as 1/10 to the first. Now, there's an interesting trick. Well, not really a trick, but if you have a number in the denominator and you want to flatten it out, you want to bring that number up into the numerator, you can do that as long as you change the sign of the exponent. So 1/10 to the first is equal to 10 to the negative first. So again, if we wanted to kind of break down 0.01, that would be 1/100th, which is 1/10 to the second, which is equal to 10 to the negative second. 1/1000th, 1/100,000th, okay, and that's 1/1000th, 1/10,000th, sorry, thank you, and 1/100,000th, okay. I think you guys are fine with all that. All right, so since this is a big number, okay, we're going to pack it up. Yeah, you guys probably, where would you tell me the decimal is in 455,000?
After the 4.
It's not after the 4. It's going to be after the 4 when we pack it up, but where is it now? The end of the zeros? Yep, I buy that. So kind of an important distinction is since somebody didn't take the ink to write it there, it's what we call implied. So I'm going to go ahead and put a decimal there for now. I'm going to put dots around it. That dot, those dots around it, it's supposed to be kind of dotted. Those dots around it means that it is implied. You know, you guys knew it was there. It's implied. So when we pack up this, actually we're going to move the decimal place over 1, 2, 3, 4, 5. Just like Caitlin said, and it's going to be between the 4 and the 5. Okay, so the coefficient is going to be 4.55, and what's the 10 raised to the power going to be? 10 raised to what power? 5th, yep. 4.55 times 10 to the 5th. Perfect. So again, this is like the coefficient. Later on in this class, we're going to talk about another type of coefficient, but this right here is the exponent part. Cool. Very good. Okay, so 0.0021. And if you're like me, I actually have to move the decimal over 1, 2, it's like I'm going to move it over 3 places to get my coefficient of 2.1. So it would be 2.1 times 10 to the negative 3rd. Yep. You got it. Okay. So then I have a couple of slides to do just kind of what I think seems like you might already kind of know how to do. If the number is large, then we need to move the decimal point to the left, whether it's implied or whether it's really there. Okay, move it to the left to get a number that's between 1 and 10 and count how many spaces you move it over. And then raise the 10 to that positive power. If it's smaller than 1, then we need to move it from the left to the right, count our number of places, and then the exponent of 10 is going to be negative. Cool. And then don't forget that if somebody is like being like, if somebody says you have to pack up this number in scientific notation and it's already between 1 and 10, okay, then basically write it as the coefficient times 10 raised to the 0th power if they're being a stickler, because that's times 1, okay? All right. So an example, if somebody was being a hard butt and said, I want you to pack up the number 3.236, you would say, okay, in scientific notation, you're like, fine. The coefficient is 3.236, and the exponent part is times 10 raised to the 0th power. There. Okay, very good. Okay, so now we have some examples. I'll give you a minute to go ahead and knock those out, and then we'll kind of compare answers. How do we do? Okay. Let's pretty good. Are you guys good with this part, where the last one, we do keep the negative with the coefficient because it was a negative number to begin with? And of course, the exponent is positive because its magnitude is larger than 1. All right. So this homework will be due on Monday. So I'll kind of take a quick look at what these look like. So we're back to chapter 2. So here they are. They're all even problems, and you can actually work the odd problems to check yourself if you want. But the first two are, come back here. The first two are packing up numbers in scientific notation, and the other are kind of unpacking numbers that are in scientific notation. Come back here. Okay, oops. All right, so these are packing. And these are unpacking. Oops. Okay. Well, that's as far as I wanted to get. I feel like I kind of went fast. We kind of introduced you to the metric. We'll be looking back at the metric when we come back. And scientific notation. Good job. Have a good weekend.